So the first question, which vector defines the magnitude and direction of lattice distortion during dislocation in crystal structure? Okay, we are given different types of vector: Peerless, Nabarro, force vector, Burgers vector, Hooke's vector, and Schmidt vector. Okay, we have to find which vector defines the magnitude and direction of a lattice distortion. Okay, that magnitude and direction, which among these vector shows? Okay, define. So among these, the answer is Burger vector. So Burger vector, as you can see, this is a representation of Burger vector. The figure on the left side is actual representation of lattice of a given cubic structure. Suppose a plane is inserted on from the top of this unit cell. As you can see, all the line, this is an assumption, it's based on a theory. Suppose I am drawing a closed figure. Okay, as you can see, the square shaped figure. So when I insert a plane on this given unit cell, that all the line get distorted. Okay, so I will not be getting the starting and ending will not be aligned to itself. So additional line or vector line has to be um, inserted in order to meet the starting and ending. That's B. As you can see from the second figure, there is a small B letter. That's a vector shown. That is a Burger vector. It's represented by magnitude and that vector is represented by magnitude and direction. Okay, so among these options, the vector which shows represent the magnitude and direction of lattice distortion is Burger vector, because I can interpret it from this given Burger circuit, right? So the answer is Burger vector. So how do surface defects predominantly influence initiation of cracks in material? Okay, we have different options. They enhance the material toughness, they act as a point of stress concentration, they reduce the elastic modulus of the material, they increase the thermal stability. So the surface defects, we have already learned it from the metallurgy. So any type of surface defects, irregular shaped pointy surface is always. So among these options, the answer is they act as a point of stress concentration. Okay, any type of surface defects is always irregular shaped surface always act as a point of stress concentration. So as you can pick that, it will initiate crack rise. So option B is correct. So which description best fits the role of Burger vector in dislocation theory? It identifies the slip plane's orientation, it measures the dislocation density, it quantifies a mismatch within the lattice structure due to dislocation, and it determines the crystal melting point. So from the very first figure, very first question, I already explained how does a Burger vector works. So among that option, you can see I already told there is a final vector is needed in order to complete that Burger circuit after distortion by inserting a plane, right? So among these options, it quantifies the mismatch within the lattice structure due to dislocation. Okay, there is dislocation due to that plane inserted. So the Burger vector, it quantifies, okay, represent the that lattice structure mismatch, okay, that shift from the actual starting and ending. So the best fit description of a Burger vector in this option is option C. It quantifies the mismatch within the lattice structure due to dislocation. Okay. So what is the primary effect of dislocation force on the mechanical property of a crystalline material? Decreases ductility, increases malleability, increases yield strength, and reduces electrical resistance. So what is a dislocation force? It is simply the number of dislocation line per unit volume. You can see our dislocation line per unit volume. So primary effect of dislocation force on mechanical property is simply it increases the yield strength. Okay, there are more number of dislocations line which will oppose the further deformation, plastic deformation. Okay, the body strength will increase. This number of dislocation, the mobility of dislocation line and strength is inversely proportional. Okay, so option B is correct because it increases the yield strength. It opposes the further deformation or plastic deformation. So it eventually increases the yield strength due to dislocation force. Considering the dislocation interaction, what effect does increasing dislocation density have on material's ability to deform plastically? Okay, this question has similar theory on. It's just like dislocation force. Okay, so I mean these option enhance plastic deformation, reduce the impact of Burger vector, increases metal brittleness, and diminishes the rate of work hardening. The option is metal increases the material brittleness. Because before that I will explain what is dislocation density. Like what this term dislocation density means, it's simply the number of just like dislocation was the number of lines in the unit volume. So more number of dislocation line means the further opposition, right? So material strength increases, and as it increases, what really happens is it become more stiff, it will become more brittle. So material will become more brittle due to further increase of dislocation line. So not um support the further plastic deformation. Okay, so it will not have a plastic deformation, it will become just like a rigid material. So when dislocation density increases, there are more number of dislocation lines as you can see in the unit volume. So it will eventually increase the yield strength and material become more brittle. Okay, so it increases the material brittleness due to increase in dislocation density. And next question is, what is the defect called when a pair of an extra cation anode added to an interstitial site in a crystal maintaining charge neutrality? Okay, so there are many types of defect. Among the one which is having maintaining the neutral, which is occurring in defect and while maintaining the charge neutrality, it is Schottky defect. Okay, Schottky defect, there are equal number of cation anions are removed from its lattice point, so it could move to interstitial site or any other position. So equal number of extra cation anion removed from any lattice point is simply Schottky defect. So when a pair of cation anions missing from a lattice of an ionic crystal, the defect is known as Schottky defect. This is closely related to a vacancy in normal crystals. So Schottky defect facilitates atomic diffusion. Okay, as you can see the basic definition of Schottky defect. According to your question, the type of defect occurring when equal number of cation and when a pair of cation anion is missing from its lattice point, the answer is simply Schottky defect. Okay. Principle explain the formation of solid solution based on the atomic size factor according to Hume-Rothery's rule. Okay, before that we have to know what is a solid solution and the basic factors are affecting the according to the Hume-Rothery rule. So what is a solid solution? A solid solution forms when the solute atoms are added to host material. Okay, we will be having host material and we are adding a solute atom, okay, of another material. So the crystal structure is maintained and no new structures are formed. The thing is happening is it will impersonate into that host material and it will not change its structure, host structure. Perhaps it is useful to draw I will show an analogy. If two liquids are that are soluble in each other, such as water and alcohol, so each one have its own composition. When they are combined, a liquid solution is produced, right? And in with that liquid solution, the solute, suppose solute to be alcohol, so it is uniformly mixed throughout and will not change the basic compound structure, because same as that of solid solution. Okay, solid solution is also compositionally homogeneous after mixing with the solute atom. The impurity atom are randomly and uniformly dispersed. Okay, which is randomly added. Okay, in a solid solution the solute atoms are randomly added but it's uniformly placed, so will not change the structure and there will not be forming any new type of structure. The existing structure and the solute atoms are added, it becomes uniformly arranged. Okay, that's simply what is a solid solution means, solid solution. Okay, so based on the solid solution, there is a rule called Hume-Rothery rule. So among that, one of the main point is related to atomic size factor. So this is one of the main point of Hume-Rothery rule. So appreciable quantity of a solute may be accommodated in this type of solid solution only when the difference in the atomic radii between the two atom type, okay, one of host material and another atom of solute type, is less than about plus or minus 50%. Okay, the difference should be less than 50%, otherwise the solute atom create substantial lattice distortion and new phase formation. So the difference of atomic radii between the two atom types should be less than 50%. Okay, so this is one of the main point of among the 4 points, this is one of the main point of the Hume-Rothery rule related to atomic size factor. Okay, so we have 4 options among that, option A is correct. Okay, I cannot choose option D because atomic radius must differ by more than 50%. No, it should be less than 50%. And the role which basically deal with related to atomic size factor and less than 50%, that's the best option, option A. Among option A and D, option A is suit. It cannot be more than 50%.